There we go. All right. So again, we're talking about three different projects here, not just the Honors College project. There's different ways to engage. Again, we've got the online engagements. We've got the in-person tours. You guys here in the auditorium toured last Thursday, and I know we had a bunch of questions coming about geotechnical and foundations, and I basically answered, we'll talk about that next week. So here we are next week with a whole bunch of answers. We're talking about foundation systems and the subsurface conditions. One of the fun things we learned out this project is, even though, as you see in this picture, even though the Honors College and the Wellness Project are literally across the street from each other, the bedrock for the Honors College is down about 100 to 130 feet, but you go right across the street and the bedrock for the Wellness Center is about 50 to 70 feet below the ground. So we're going to have one speaker that's going to talk specifically to that. So we've got Brian Wilson, who is not here. So we won't talk about Brian Wilson. We've got Dylan Richard, who is here. He's a structural engineer. He's got about 21 years of experience, and I've probably worked with him for at least 15 of those 20 years, at least. Probably as many as that. We go way back. So we also have James Nesbitt with Terracon, the only guy dressed up with a coat today. He is a geotechnical engineer. He is also a two-time Bull alumni. So welcome him. He's got a bachelor's degree in civil engineering and his master's in geotechnical engineering. We've got Jim Maraday over there. He is he's a senior associate structural project manager, another Midwestern corn-fed boy from Champaign-Urbana, Illinois. He's worked on the music building. He's worked on the Yingling Center, the basketball practice facility, the baseball softball complex, and now also working on the indoor practice facility. So he does a lot of sports type project. He's also got a lot of experience here on the USF campus. We've also got Bill McNally. He's an associate structural engineer. He does a lot of healthcare engineering, a lot of educational K through 12, all the way up to higher education. He is the structural engineer for the Wellness Center. We've got, for the Wellness Center, sorry. Alex Biggs, who is another principal. So one of the strange things that we've got is we have 3 different projects, 3 different architects, 3 different contractors, but the same structural engineering firm across for all of these. So that's kind of a unique thing, but we'd love to have Walter P. Moore. They bring a lot of experience to our projects. So Bill McNally, we've got Alex Biggs, who is the structural engineer for the Honors College. He's got about 17 years with Walter P. Moore. He's inspected a lot of projects. You know, he's wearing blue jeans. He gets out in the field. He's not afraid to get things dirty. And Evan DuPont, who doesn't have blue jeans on, but he's got a different color jeans. He is our superintendent, and he's the guy that helped us with our tour last week and with the other guys. We're going to follow up with a bunch of interesting stories from the field that Evan's going to share, and then also some question and answers. So just go ahead and hold your questions, and if you're online, we will monitor those. And we're going to kick it off with a poll right here. If you're in Teams, go ahead and let us know. That way these speakers know exactly who you're speaking to and who we do have online. So that'd be great. With that, I'm going to pass it right over to Dylan Richard.
I'm going to put this so I don't have to keep track of it.
Okay.
There we go. All right. Do we need to give a lot of time for the poll here? Or are we good?
No, it should be.
Okay. So why are foundations important? Well, the foundation is your base, right? It's what everything's supported on. You hear that sometimes, that that's my foundation, my rock. That's what supports me. Well, the foundation is what supports our buildings. Without it, the building will just keep going through the ground. So every structure needs a foundation, obviously. At Walter P. Moore, we don't design these type foundations, but a foundation is something that supports your building. And the design is so very important, because if your foundation doesn't perform well, you could have damages to your building. So if your foundation is not good in some areas of the building and it is in others, you might have settlement. These walls may crack, or the bricks on the outside of the building might start to fall apart or crack. You can lead to distress in the structural frame that's supporting everything, and even into failures. So foundations is really the very first thing when you get out on a job site that sets up the success for your building. And the repairs can be very costly. This is an example where a building was starting to sink a little bit, and they had to come in and build something new up underneath it to get it to keep from falling down. So the design steps for a foundation, it all starts with the geotechnical engineer, and you're going to hear from James in a little bit from Terracon, and they are the experts in understanding the soil and recommending to the structural engineer, the design team, what type of recommendations or what type of foundations are good for this particular project site. Like Steve mentioned earlier, the USF Honors College, its foundation system, as you're going to see, is vastly different from right across the street at the Wellness. And this is all comes to us as the designers from the geotechnical engineer. Once they recommend the types of foundations we can have for our site, then we, the structural engineer, we have to establish how much load is going to go down. So what's the building weigh? And with all the people in it that occupy it, how much load does that foundation need to support? Once we have that, then we can go in and actually do the calculations and design our foundations. So today we're going to talk about 3 types of foundations. There's a shallow foundation, a matte, or a deep foundation. Now, the shallow foundations are usually the most cost economical. The matte foundations and the deep ones usually get a little bit more pricey, but they're usually necessary when there's really poor conditions on a site. So shallow foundations can come in 3 different types: isolated, combined, and stripped. The isolated ones are the ones that support just a single column. And you can see in the diagram here, a combined would support multiple columns and or columns and walls. And then a strip footing is just a continuous piece of concrete foundation that would support a wall. So here's a good example of an isolated footing. You can see there's the hole in the ground for the design size and thickness, and the rebar goes in there, and then they pour the concrete, and then it's ready to receive the column above. Here's an example of a shallow combined foundation. Same as the other one, the previous one, only multiple columns or columns and walls would be bearing on it. And then this is an example of a strip foundation under a wall. Again, on the left, you can see instead of just one square or rectangle under a column, it's continuous, and then the wall would be laid out over the top of it. The next one is a matte foundation. So this area of Tampa is very prone to sinkholes. And the sinkhole oftentimes forms if there's poor soils or there's actually voids in the ground. A matte foundation is essentially one large spread footing over the entire building. So as you might imagine, that's a lot of concrete. So this is where your cost really starts to go up. And it's also a lot of rebar, because we have to be able to take all these point loads coming down from the columns and spread it out over the whole building area. And then next would be deep foundations. In this case, the upper layer of soil just beneath the ground is usually very poor, and we got to get down to hard rock or hard layer of shell. So here what we do is we essentially put columns in the ground. They're called either piles or piers, and then we put a cap on top of them that we send our columns, that we bear our columns above ground on. So deep piles or piers can come in a variety of sizes and types. And this is usually we usually design these based on the material availability and the cost of the market at the time. Sometimes it's designed around the contractors that are available to install them. The three on the left, the non-displacements, those are ones that we actually go in, drill out the soil, and then fill it. The ones on the right are displacement ones. These are the loud ones. If you go by a job site and you hear this hammering going on, boom, 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 these are ones that they actually set up vertical and they pound them into the ground till they get down to a layer that's solid enough that it won't go anymore. So those are the foundation types. Here you can see on the left picture is some drill piers that are already in the ground awaiting for the cap. And then on the right is the rebar going in for the cap to be poured. So with that said, I'll turn it over to James, and he's going to tell you a little bit about what he does up front as the geotechnical engineer.
Good afternoon. So yeah, just kind of playing off Dylan. He kind of touched base on a lot of the foundation stuff, but my name's James Nesbitt. I'm a geotechnical engineer with Terracon Consultants. It's a large national firm, pretty much all over the country, really. So we get to, as a company, we have to deal with a lot of different soil conditions, but in particular today, we're going to be discussing kind of the soil conditions we deal with here, specifically at USF. You know, maybe east, I'm sorry, west Florida, Central Florida kind of deals with it, but USF specifically. Oops, wrong way. All right, so what is geotechnical engineering? I think that's a good starting point for our conversation because usually when people ask me that, I wonder how deep down the rabbit hole I want to go with that description. But basically what it is we get involved early on in the site. You know, before a lot of these guys, usually structural's on board by then, but and our job is to go out and study the soils so that we can develop ultimately foundation recommendations. Every job is different. You know, we have national accounts with, you know, anything from a Chick-fil-A to in downtown Tampa. If you've gone through, see all those high rises going up. We're working on those as well. So to accomplish the studies, we have different tools we use or different types of tests. The rig you see over there, the yellow portion is the rig. It's mounted on a truck. That's an SPT rig. Typically, that's the kind of the go-to, the common one we use. You know, the reason we like it so much is because it gives you a soil sample and it gives you a soil relative density. So you're getting two things out of the test. You know, other options that we have are CPTs, which is a direct push method. You're not getting any sample out of it, but you are collecting a lot of data. So sometimes we'll mix and match or use both of them if the sites are really tricky. So that really helps out. Geophysics is something we use as well. Probably discuss it a little more on the next slide, but you know, there's a lot of reasons you would use geophysics, especially ground penetrating radar. You could have buried debris on a site, like old farms. They usually have buried debris. Farmers like burying all kinds of stuff. You know, as Dylan mentioned, sinkhole conditions is kind of big. So we'll run GPR to kind of help determine if there's any anomalies, which an anomaly is in essence a break in the stratigraphy. So they'll show some down warping of the soils, and then we'll usually go test that with an SPT. You know, laboratory testing, once we collect the samples, you know, obviously we can do different types of tests with the soils. They usually help out with different aspects of design and whatnot. And then we use a lot of our judgment and experience, and that kind of ties back into, at the top there, it says art and science, which it's kind of weird to say art with anything engineering, but a lot of times in geotech, we don't have all the, you know, we don't know all of our properties because the soil varies. The testing is kind of limited for the size of the site. It's not like Dylan, who knows the values of his steel, knows the values of his concrete. You know, we're having to make some assumptions, and there's some finesse with that. You have to kind of fill in the gaps. So what it comes down to is understanding your structural loads. You know, we'll assume them a lot of times because we're involved so early. We'll kind of know what kind of structure is going to be built, and we'll make some assumptions based on our experience. And then the soil conditions, and that's what we go test for. So here, getting specific to USF, and kind of like I said, the west central portion of Florida in general, it's known to be very karst. If you guys have never heard that word, it basically is a landscape where the, in our case, limestone is undergoing dissolution because of the water that runs through it. You get basically porous limestone, the cavities get larger, you get caverns, you get caves, you get eventually what would become a sinkhole potentially. So, and like I said, the GPR helps us identify where that's starting to happen, especially if we'll scan maybe the building footprint and make sure that our building's not going to be built on something like that. And then these blue dots here, just projects I worked on over the years. You can see where all the clusters, kind of Pasco County, Hernando County, and kind of that USF kind of area. So it's quite a bit of them. And then that middle picture there is, that's in Lecanto, which is up near Crystal River. You can see a cave kind of opened up right below that tree. And then that boulder over there, I think that's still on the USF campus. That's limestone, that's what it looks like. It's very porous, looks like Swiss cheese. And like I said, it kind of wears out over time. Geologically, it's very young. Our geology is very young compared to up north where you have granite and stuff like that. So
are those projects that you worked on, or those?
Yeah, the blue dots. Yeah.
You worked on that have sinkhole.
They're sinkhole projects. Yeah.
Okay.
Yeah. Now, I mean, you can get into like what level of sinkhole it is, but it's a story for another day, I guess. But. Yeah, it's funny, not to jump back, but I always get friends of mine asking me when they're trying to purchase homes, what's going on here, but I need to start charging for that. But so anyway, so this is kind of specific to the USF area. Here's kind of known sinkholes that occurred, likely either randomly or during construction. You can see that on campus there's been quite a bit. I'm not going to get to it too much into it in this talk, but usually the way we deal with it is by grouting. I don't know if you guys have been exposed to grouting or whatnot, but if you get if a sinkhole opens up on site, we'll go try to collapse it, backfill it, generally run something like GPR, try to identify where the throat of it is, and then set up a grouting program, which is pumping grout either right down the middle and then radially out after that, just kind of recreate the surface of the limestone. So kind of tying back into Dylan's presentation, I didn't mention map foundations on here, but that is also one of the options. But these three kind of pertain to the three structures that we're dealing with. Shallow foundations, as he mentioned, you're bearing on the upper soils basically. So anything like a home, a small a restaurant, in this case the USF indoor facility is going to be on a shallow foundation. And then next you have shallow foundations with ground improvement. That's where, the soils can't quite take the load of the structure, but you don't want it to get so expensive that you're trying to do deep foundation. So there's a kind of an in-between, and ground improvement is a good option for that. Vibro replacement stone columns is pretty much the go-to as far as that goes, and I think the Wellness Center is using those. And then there's deep foundations. As Dylan mentioned, you got to transfer the load down to a better competent layer. So the USF Honors College is using that. So you have three, very different buildings, three very different foundation types, all within, 2,000 feet of each other, basically. In this case, right across the street. But, I think Jim's going to talk a little bit more now about the indoor practice facility. I think we worked with them on the Bucks indoor facility as well. So pretty similar building, if you guys have seen that, driven by the stadium. But yeah, but with that, I'll let Jim kind of give you details.
All right, so as Steve mentioned, I am a design project manager for the indoor performance facility. I've worked on a bunch of projects here at USF. Those familiar with campus, the the new facility is going to be over off Sycamore Drive. Basically, historically, there's been 3 outdoor practice fields, so we're taking over one of those. James and Terracon did do the geotechnical engineering over there, and soil is typical for campus. Pretty sandy, clay, limestone down, I think about 40 feet or so. But this type of structure is fairly lightly loaded. It's not a very heavy structure. So we determined that based on the loads, we could get away with just a shallow foundation system. I think they discovered one anomaly on the site. It was about center field, maybe 30-yard line or so, that they're going to be doing some further investigation. The site work, I believe, is intended to start here in the next couple of weeks, end of October or so. 27th of October, okay. Then shortly after, November to February or so, with intended completion of the project towards the end of the year next year. So building itself, I won't dive too deep into the structure, but it does drive a lot of the foundation design. So it's going to be a metal building. A football field is pretty large, and so to be able to economically cover that, a metal building is kind of a great option for that. And when I say metal building, it's basically a bunch of frames that are spaced out a certain distance that can span 200 feet of width. And so we see that over here on the left side. This is looking from the current practice outdoor fields. And then there's also a secondary structure attached to that that's kind of an entry and meeting rooms, things like that. So here's a 3D image from our model as engineer of record. We kind of lay out the basis of design for the metal building frame. And so essentially we have 30-foot bay with the frames that I mentioned that are tied together laterally. What we're not seeing here is all the purlins that would span between those that carry the roofing and the cladding. But again, pretty light and efficient structure. So here is kind of the foundation plan from our issued for construction documents. And so what we have is, I don't think I can point here, but basically at every column line, we've got 10-foot square shallow foundations at the end of each one of those frames that are tied together with a grade beam that run along the field. And then unique to this type of structure, we also have a continuous, what we call kind of a tension tie grade beam that runs beneath the field from column to column. So the grade beams it's essentially a continuous strip footing that ties those spread footings together. I'll show some details here in a couple slides. This is the frame, and I like to point this out because it kind of drives the design of that grade beam. Essentially, from grid A to M, I think it's like 208 feet or so. And from the field level to the apex of the frame, we're talking 68 feet, so pretty large amount of space. And even though the structure itself is not real heavy, there is some roofing on there. There's some roof load that by code we designed to. So even that little amount of load is going to cause this 208 foot wide frame to want to flex. What happens is that creates a huge outward thrust force on both columns. And so to resist that, via foundation system, you could, if we had deep foundations, you could do kind of like a battered lateral pile, but we don't have that here. You could use like a slide friction resistance on the foundation, but to do that, you generally need a pretty large foundation, and so it becomes not very economical. So what we ended up doing was using these grade beams that tie the two columns together to essentially resist and balance out that huge thrust force that ends up occurring. And so that's what each one of these, the purpose of each one of those is.
You know what I'm saying, at the bottom, so we'll tie them together.
Yep, that's right.
Just off the thrust out.
Yep. So here's a couple details from our issued for construction documents. The metal building columns bear at the field level. So our foundations are down 2 feet, which is where our square shallow foundation is, and that's where our continuous grade beam across the field is, which is coming in from right to left. So to get down from the field level column bearing to our footing, we have to have basically a small 2 foot deep concrete column. And so that occurs at every single one of these metal building columns, a whole bunch of conventional rebar to get that big thrust force from the field level down to the foundation. We have a whole bunch of developed bars. And then on the right side is a detail of the actual tension grade beam itself. In this case, we have it's 2'6" by 1'6" deep, continuous, 6 number 8 bars, top and bottom. And the key here is that we call it spliced. A coupler that occurs when 2 bars come together. 8-foot piece of rebar to the site. So it comes out with probably 3 or 4 pieces, and so they have to splice these together. Maintain that continuity, we use mechanical splices. So as James mentioned, unfortunately this project is not under construction yet, but we did do the Bucks practice facility, One Buck Place, over on the other side of town. And it's essentially the same exact foundation system. It's a metal building as well. So here was, before they poured any of the foundations, these being essentially the concrete columns that are taking the load from the field level down to the foundation system. We've got continuous grade beams in this direction. Can't really see it here, but the square spread footing, and then the continuous tie beam that would run under the field. And then on the right side here is one of those continuous tension tie beams. On the left, a little zoomed in photo of where mechanical splices that I mentioned earlier, couplers. Basically just screw in on each end and create that continuity. And then on the right, just another image showing those continuous tension bars coming right in the column cage and everything getting. And then a little bit further along during that construction, everything has been poured. Anchor rods have been set for the metal building columns. Everything ends up being nice and clean. Can't see any of those grade beams. And then on the right, it's kind of the finished product with the column at the field level and the turf there right up against that. So here a little poll question. What is the purpose of the grade beam tension ties across the field? Was it to keep the field level, to bridge the soil anomaly, to resist the field gravity loads, or to resist the lateral shear forces from the metal building structure? All right, and with that, I'll hand it over to Bill McNally.
All right, I'm Bill. I've been with Walker Moore for 6 years, like Steve said, and I was one of the engineers on the Student Wellness Center. So we had 2 parts for our soil improvement. The first one was ground. The second one was stone columns. So first one was grouting, and the main purpose of this is sinkhole prevention. So the geotechnical engineer will identify a certain area on our site that is prone to sinkholes, and then they will provide a drawing, which you can see in the upper left corner, showing where or how to grout the soil and where to provide grout pipes in order to grout the soil. And in the lower right-hand corner, you can see the grouting pipes installed in the field matching the same grid pattern that was specified by the geotechnical engineer. And the whole purpose of this, as I said, was to prevent sinkholes from opening up on the project site. And they just identified this one location as prone to sinkholes. The second part of soil improvement was Vibro Replacement. And basically the purpose of this is to increase the strength of the soil so that you can put more weight on the soil. At the Wellness Center, the initial capacity was going to be 3,000 PSF. And with stone columns, we were able to increase that to 6,000 PSF. The reason this is important is it helps you reduce the size of your footings. So it helps save you on the amount of concrete that you need and also the amount of rebar you need within that concrete. The way this occurs is, unfortunately, we don't have a picture because this has not begun at the Wellness Center yet. But the purpose of it is to densify the granular soil. And you can see on the right, what they do is they drill a deep hole, and they have a big stone pile that they take stone from and inject it into that hole. When it's getting fed into that hole, it'll vibrate the soil, and then that causes the stone to kind of go in between the different grains of the sand and make it a much denser soil, so then it's a stronger soil also. So as you can see over on the right side, it starts empty and then it starts filling up and vibrating the stone into it until you get a stone column that gives you the additional bearing strengths.
Actually go over to the Wellness Center project. On the north side of the site, they've opened up the screening. You can actually look, and they're actually doing the Vibro
Okay.
Right now, this week.
Okay. Yeah, I know they were doing grout a couple weeks ago, so that makes.
They finished that last week.
Okay. So we did spread, once you have the stone columns, we did spread footings on top of that soil. And what spread footings essentially do is they distribute the load out to the soil. So it's a little bit of a different mechanism, but you kind of think of this almost like paddleboarding or surfing. If you're just trying to stand on the water, you're going to sink through the water. But if you're on the board, it helps, gives you a bigger area to stand on, so it helps you stay stable and not sink down. So on wellness and most projects, when you do spread footings, you're going to have two different conditions. You're going to have one that's only gravity footings, and those are the columns or walls that only take the weight of the building or the weight of the people in the building. And the other type is have gravity and lateral spread footings. And the difference there is you have the lateral force, so that's from like a hurricane blowing on the building and wanting to move the building or essentially uproot the building. So this is from our 3D model. This is what the Wellness Center will look like structurally. This will all be covered up, so you won't see any of this. But mainly focus on the footings down bottom. And then on this project, these are all the spread footings that are only gravity. So most of our footings are gravity, and they're not lateral. So I'm going to do real high-level spread footing design for gravity only. But essentially, you size the footing to be for the length and width of the footing to help you distribute that load, so it basically doesn't sink through the soil or settle more than you want to settle. So that's how you get your area of the footing. And then you design the thickness of the footing so that you basically don't have the column punch through the footing. And you kind of think of this like if you've got a piece of paper, like a single piece, and you push a pencil through it, it's going to break right through that piece of paper. But if you have an encyclopedia or something like that, and you try and push the pencil through it, it's so much thicker, you're not going to be able to punch through it. And that's how you design the thickness of the footing. And then you add in reinforcement to basically help you resist the bending force that occurs from the soil pushing up while the column pushes down. So on the wellness project, we only have 3 footings for lateral. And those usually, in most buildings, will occur underneath of elevator walls or stairwells or just areas, in our case, where you have concrete walls that go all the way to the top of the building and then go down to the footings. And the lateral spread footing design is similar to the gravity spread footing design, but you also have the additional requirement of resisting the lateral loading. This is much more complex, so just simplicity-wise, I'm going to say the 2 purposes are to prevent the building from wanting to overturn. It's kind of like a tree wanting to uproot itself, and the other is just preventing the building from wanting to slide while the wind pushes against it. And spread footing analysis in our engineering practice, we'll usually do initial checks early on in a project to get rough footing sizes with just Excel spreadsheets or just rough hand calcs, like pressure over or force over area to get the bearing pressure. But once we want to really redefine our analysis and get a much more economical solution as the project progresses, we put it into a 3D model. And in that 3D model, we can get out, as you can see over on the right side, it'll give you bearing pressures for both uplift and gravity. And then it also will help us determine the amount of reinforcement that's needed in each footing. So then we can determine how many number 4 bars or number 5 bars we need in the bottom and top layers of the of each footing. So that's a real high level of what spread footing design is with soil improvement. The main purpose of the soil improvement is just so you can reduce your footing size. And then as you go into the design, you initially start off with some hand checks, and then you graduate to doing a 3D model. And with that, I will hand it over to Alex Biggs to talk about the Honors College.
How y'all doing? My name is Alex Biggs. I was a bull. I graduated from 2002. I think some of the same professors are still here. I had Nora and Mullins, and I worked at the Perkins right off campus that I think just recently closed. I was a waiter. I went up and did my master's at a school further up north in Gainesville and did research there. But I had a great time at USF and learned a lot. Yeah, that one, Santa Fe, exactly. I worked on this project, the Honors College. I'm the office design manager for the Tampa office, and I'm one of our senior PMs. I try to split my role. I work with a lot of young engineers on projects and work as a mentor for them. So this is our Revit model for the Honors College project, and I think we're going to go into more detail in a later seminar. We're talking specifically about the foundations here. So we're going to talk about deep foundations on this project, which you can see are pretty deep. That's why they're called deep foundations. They're drilled shafts, drilled piers. And let's get into more about the project. I'm showing here the architectural design. It's kind of how it starts. This is a really developed rendering on the project, but it starts with the architect who's producing a watercolor to try to have a good vision for the owner, for the future tenants of the building, to like the visually and then use, and you want something really nice and impressive. So this starts out literally like can be a sketch watercolor, and then this is the final renderings that we go in and actually try to figure out how to stand up, how to structure. So our structural design starts after that. Here you'll see our geometric model, our documentation model where we're in Revit. We're modeling all of the structure, the bones that help the building stand up. This is obviously advanced, far along. On the right is our analysis model that Bill was talking about. We have interop programs that we've developed that go between Revit, and this is ETABS, an early version of our ETABS model, where we actually are going in. We don't want to just button push, so in an analysis program, the analysis program goes in and does a finite element analysis. We put loads, lateral loads, gravity loads, like Bill was talking about. And then through finite element analysis in the program, it will load up the columns, beams, and shear walls and provide a reaction for us to design the foundations for. So right now, our long drilled piers are just modeled by those little pins you see at the bottom of the column. So we have to go through our full analysis to get the final reactions. Stepping back a little bit, we start out with the geotech really early on. So we're going to get an idea of the size of the building and anticipate like the column loads that are going to be on the building. And so we provide those to the geotechnical engineer, Terracon, and they'll go out and do their borings for the project. So after they do their borings, they go down, do sampling of the soil 100 feet down. they'll get the number of blow counts that was required to go through the soil for each layer. So if it takes, 30 blows to go through one layer, we know that that was a nice dense layer, or 60 blows. At some point, they'll hit refusal, and that's when we know we're down to rock. So that was pretty deep on this project. There's an example that then they go on to make their recommendations for the project, which foundation types we should use, whether it's shallow foundations or deep foundations, like we were talking about before. On this project was deep foundations. So we took their criteria, their recommendations, and we put it in. This is in our documents, in the structural documents. We've referenced the geotechnical engineer report and the recommendations for the size of the drilled piers on this project. And then out there is our design of the drilled piers for the project. And they varied in size from 2 feet to 3 foot in diameter. And we had estimated lengths early on with the length there, 80 to 90 feet deep, the estimated embedment into rock based on how much capacity we needed for each pier, and then the anticipated load you'll see on the right. So those are in kips. So 1,000 kips is 1 million pounds per pier. One kip is 1,000 pounds. Yes. And interesting on the site, like we were talking about with Geotechnical, the sinkholes. I've had other projects on campus where we had a sinkhole open up at Student Healthcare Center. And so we had to account for a certain amount of extra concrete because voids open up as you're drilling down. So we had literally just put in that the contractor had to account for 2 times the theoretical volume because we're literally filling the ground with concrete to try to make it all solid down there. So I think at the end, we ended up at like 180%, so a little less, but if that wasn't accounted for, then that's a huge difference in cost for how much concrete would be needed for the foundations. I ended up here with the detail that we had for the project for the Augercast Piles. So this is a nice little short version of the long drilled pier, but there's a reinforcement cage that we designed for. You saw it in the schedule, and it goes all the way down in the shaft, and then they pour the concrete in, and it gets instrumented with like strain gauges and other instrumentation so that we can monitor the in-place stresses. The geotechnical engineer will often monitor the in-place stresses, and when we're doing the testing for the drilled pier, we want to be able to see how much stress is in the pile or the pier during that in-place test. So we're going to go to that next. We have all these theoretical ideas about how much capacity these piers can take. There's skin friction, end bearing, and then we always make sure to do one test on each project. So we test. There's different ways to test. There's a nice controlled manner of testing, but Dr. Mullins on campus was doing research, has been doing research for the last 30 years on Statonamic Tests. I don't know if you guys have heard of that, but it's basically a controlled little explosion that forces the piston down and sends a little uniform force down onto a test pile, and then you're able to measure how much displacement. Let's see. Oh, there you go. So after that, that sends a force down that you're able to, with the instrumentation that's in the pile, make a displacement, a force displacement curve. So you can predict how much it's going to move by how much weight it has in the final conditions. So that's a way to prove what was the assumptions in the geotech report. That sounds right. Yeah, I know they vary. Nice. Right, right. That'll produce a curve that instrumentation data logs, and then we can interpret that. And it's not structural engineers; it's the testing company and Dr. Mullins and people like that. They'll go back and fit that to a nice displacement curve that we can use to confirm like our assumptions at the beginning. Ooh, I had it. Okay, so with that, I'll turn it over to Evan. Thanks.
Nice work, nice work. Let's see how to click this on. Okay, guys, I'm Evan DuPont. I'm with Beck. We're the construction manager at the Honors College. I actually have a colleague in the back here. Chris Clater's our senior project manager. He's here to support me in case I develop laryngitis halfway through, which could happen anytime, right? So the good news is I'm not a structural engineer. I'm not a professional engineer at all. Bad news is I'm not a lecturer either. So bear with me, guys. But really the idea of my portion of this is to take all of the textbooks that you just saw and bring them to what it actually looks like. A lot of times that's easier for people to understand, and you know, the picture's worth 1,000 words thing. Kind of talk to you about what happens on site after these guys. They're not done with their work necessarily, but they've done, you know, the lion's share of their piece of the work. So some of this stuff is going to be a little bit repetitive, and I'll try to breeze through that stuff, but I might be showing it from a little bit different perspective. So first thing, before we actually put foundations in the ground, you guys saw a lot about this already. We had surface anomalies on our site, just like much of the campus, much of the area. And those were identified during the very preliminary geotechnical studies. So the map you're seeing on your right, my left, is kind of a map of what those anomalies look like. That was created using ground penetrating radar. Okay, so it is limited on the capability of that equipment. This is actually an output from the GPR, and they tell me this is what an anomaly looks like that would be indicative of a future sinkhole. So you're actually seeing a strata that starts to take a dive, and that could indicate a sink, basically. And what that is, that's a type A anomaly. The blue areas are what you see. Is where that's happening. Now, when this happened, this was very early in the process, so you can see they kind of mapped out the building footprint, but that wasn't finalized. The foundation locations themselves were not necessarily finalized. And so what has to happen next, once they've identified that we were using deep foundations, you know, we've got the drilled shafts you guys heard about a few times. They finished the structural design, and what you see here is an overlay of the actual building foundations. My laser doesn't work, but every one of these indicates an actual building foundation. It's supporting a column. Some of these are supporting shear walls. And they're going to use, I don't know, you guys can read that stuff, but basically what happens here is when you overlay this and you see we've got major portions of the building that actually support large portions of our shear walls right on top of this void, that's when you say, Houston, we've got a problem. So this basically confirmed the need to further address these anomalies before we got to the deep foundations. And you already heard about grouting a little bit. That's what we used here. It's low mobility grouting. Basically, that geotechnical engineer, after he's performed these pilot borings, seen what the strata is, identified where the anomalies are the worst, he'll identify points for that grout injection. Some of the guys mentioned that. On our project, we started with 15 primary grouting points. And this is that area of the building where that anomaly cuts right through. So it makes sense that that's where we'd be grouting. Basically, each point, I kind of want to show you how everything looks. So pretty small equipment for that operation. It's not very impressive. But basically, they come drill the point in, install a casing. It's a 3-inch casing is what we use, and it'll install it to the depth that the engineer has specified. And then they're going to inject some low slump grout through that point. So this is basically a jack that they're going to use to lift that casing back out. And when I say low slump grout, the slump of concrete or grout, think of it as how runny it is. Okay, so if you poured it onto the ground, is it going to stay in a pile or is it going to run out, right? And because we don't want to just fill the entire earth with grout, we're going to use a low slump. It's a 3 to 5 inch slump. And so it's not just going to continue to run into every little crevice. You're just going to fill the major voids. It is pumped under pressure. What you can see on the right is a truck. It looks just like any other concrete truck, but it's got a grout mix in it. And they're pouring it into that pump. And they're going to inject this grout until the design criteria is met. So what is that criteria? It's based on the depth. We already know that. They're going to go as deep as they're told to. They're going to measure the temperature and slump the whole time. They have geotech monitoring the entire operation. The pump stroke count is important. So that pump hits, pump, 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 right? And why is the stroke count important? That's how they're measuring the volume at each depth. So every single day they'll calibrate that pump using basically a barrel. You know, it's very scientific. They have a known volume barrel, and they'll pump grout until it's full, counting the strokes. And now we know every stroke of that pump equals X amount of cubic yards, right? So as they're pumping, there's literally somebody counting the strokes, and they're calculating the volume based on that. They're also calculating or monitoring the grout delivery pressure. So this stuff is getting injected with the pump under pressure. And the way they set their basis is they basically use the non-restricted pressure, because it's going to have some resistance anyway if you're pumping it on the ground. What is that PSI that's the pump is reading without resistance from the ground? That's now their baseline. They measure the increase to know when they have filled in elevation, basically. So they'll pump at an elevation until they meet the criteria. Then the geotech will say, okay, come up 2 feet, do it again. Come up 2 feet, do it again. And that's how because really we don't know where that anomaly is, right? We know it's underground, maybe at 100 feet, it may be at 95, maybe at 80. So you've got to keep climbing until you've filled this one, and then maybe you filled this one and filled this one. So until we're out of the ground, they say, okay, this hole's good, move to the next one, right? Now, one of the restrictions is you can only put 20 yards in one grout point per day. And that happened a lot. Okay, so you hit your 20 yards on a hole and say, all right, done. You can either move to another hole or you're done for the day on that hole anyway. So
why 20 cubic yards?
Because it was prescribed by one of these guys.
So what you do is you pump it, let it set. So you can keep pumping under pressure, you can keep pumping the stuff into the ground, but who knows?
Might never stop.
What you want to do is you want to give them a tap so they can pop, come back and hit it the next day once they've got a chance to set up.
Let it solidify a little bit. It's to save you money, Steve.
Sometimes we do one truck, 10 cubic yards is one truck, big truck you saw there. In their case, this one was 2 of those trucks.
Thank you. We have a question. What do we have? Okay, concrete volume is typically quantified in what unit of measurement? Cubic feet, cubic meters. This is America, okay? We don't use metric systems. Cubic inches or cubic yards? This is 10 cubic yards? Okay. Interesting. Uh-oh. All right. All right, so easy peasy. We've got 15 primary grouting points. We'll move through them, get them done, right? Get to number 15, and really don't go in that sequence, but we get to the last one and we're done, right? No, never done. Then the engineer evaluates what happened at each of those. Okay, this one took a little more than I thought. Maybe that means there's some more, a larger anomaly. Might need to explore that area some more. So what he does is he says, okay, here's 6 more secondary points. And again, he said, hey, this area took a lot more grout than I thought. Let's find out if there's more void to fill. Okay, so then we go through the secondary points, and he says, almost, here's some tertiary points. That could go on and on and on. In this case, that was where we stopped after the tertiary points. So at the end of the day, this took 5 weeks on this project. And again, until you get through it, you don't know when you're done. Okay, so you can't say, yeah, we're done after 4 weeks until we get the next set of points, right? We wound up filling the ground with about 720 cubic yards of grout. Okay, so If you're looking for a place to stand and avoid a sinkhole, that's a good bet. It's pretty solid. Concrete, and this was actually covered, I think, in somebody else's slide. Concrete typically provides sufficient capacity for compression and tension. Is that true or false? No, in that football field, they put a lot of rebar in there for the tensile load that was pulling out, so that's a hint. All right, now we're done with the grouting, right? We're ready to put our deep foundations in. Our project had drilled shafts, right? Not displaced, they are not displacement. We are drilling them. Here's kind of what I always think about with these deep foundations. It's kind of that iceberg effect, right? Where you got this huge mass underwater that's much smaller than what's on top. Maybe we call it the Titanic effect. I don't know. My cool animations are gone, but I mean, our building really does fit that mold, right? So you've got basically a 95-foot tall structure-ish above the ground, right? But I have a 135-foot column underground, right? And that's this long guy right here. You can actually see in the model, it's the same one Alex showed, but you can see they're all different. And that's all based on those pilot borings. So they don't just say, okay, make them all 100 feet. This one's got to be 135. This one's only got to be 60. It's all depending on what's underground and what the load is it's supporting. This one might be 5,000 kips. That one might be 1,000, right? But it's interesting because we had rebar cages for these columns that are way taller than our building, you know, and that's why everybody sees the operation and says, man, that's a tall crane, and I don't see anything vertical happening. Well, it's happening, it's just in the negative, right? So here's a nice little aerial photo that really shows you, it's a little bleached out or washed out, but it's got everything you need for these drilled shafts, right? So right here, front and center is our drill rig. And we'll see some up close shots of that. Got to have a crane, like I said. I've got some really tall stuff to move around. And we've got some casings sticking out of the ground you can't really see. We'll talk a little bit more about those. I've got my rebar cages. That's your steel reinforcement. I got some trimmy pipes laying down. Again, hard to see, but this is really all the equipment you need. I've got a vibro hammer and a power pack. That's the big hammer that we're going to hear shaking, and it pushes those casings in and pulls them out of the ground. Concrete pump is actually there, so we're ready to go on this particular day. We got lucky, right? All right. I'm going to show you how we do these things briefly and give you a better idea of what it looks like. So the first thing we do is we put in a temporary casing and we use a vibro hammer. That's this big green thing hanging from the crane. And what it's going to do is grab onto the top of one of these steel casings, and it'll physically vibrate. It's connected to this big green power pack that's providing the power for that. It'll vibrate it into the ground until it slowly sinks, right? And that's how you put it in, and you actually take it out the same way. You'll see them use the same thing on sheet piles. A lot of times when they're doing highway projects, you'll see that on the side of the road, right? And, you know, we talked about the noise, or somebody did, about the pile driving, which is not what we have. And that's more of a bang, bang, bang. That's loud, okay? And it moves the ground, and you can feel it all the way around the site, sitting in the trailer. It's, you know, vibrating casing. So it does make a lot of noise, makes a lot of vibrations. We take a lot into account to plan that work and really survey the surrounding areas, make sure we're not impacting anybody with those vibrations. If we were doing a laboratory next door or something like that, we might have some issues, right? Where you can't have that kind of vibration. So here's our drill, right, that we talked about. And what you'll see is the casing set in the ground here. And he's actually drilling through the middle of the casing. So the casing winds up a little bit oversized for the design diameter of the caisson or the pier. And that's so he can drill right through that casing, and then he'll pull that dirt out. It's got an auger bit on it. You can see in the right-hand side picture that looks like a drill bit. That's pulling that dirt out, and then he'll clean it off. So we're basically drilling out that shaft into the ground, into the dirt. So why do we use a casing? Well, it's because we've got all these weak soils, right? So if you drill a hole in the beach, or stick your finger in the beach sand and pull it out, is the hole there? Not happening, right? So the same thing happens with all of this unstable ground that's above the solid rock. Okay, so that casing is holding that dirt from caving in, and that's its pure function. Hold the soils and dirt until we can pour it with concrete. Now, what that means also is at some point we reach substrate that will hold itself. It might be lime rock, it might be a layer above it. So that casing does not extend all the way to the bottom. It's, it might be 80 foot of casing on a 110-foot hole because that rock's going to hold itself, right? The technician with the tape says he's checking the depth using highly advanced equipment. So does anybody know what that is? It's basically a nylon tape measure, and they take a heavy piece of metal and tape it on it to weigh it. That's all it is. It's not rocket science. But what he's doing is he's checking that depth. They drill the hole, he comes and checks the depth. No, 3 more feet. They drill the hole, he checks the depth. Okay, you're good. Rebar cages are already tied, they're sitting there waiting for us. Now that the hole's drilled, the hole's clean, they actually, in our case, fill it with water. There's other ways to do that, to displace the soils. We fill it with water, but either way, you got a clean hole, you want to put that rebar in and get it filled with concrete. So the rebar is on the crane, it's on the hook, we're ready to put it in. And again, this is why we need a tall crane. So this is probably that 130 footer. It's huge. You can see that cage. All of that's going underground, okay? All going away. But that's massive. And really, what's interesting, they don't have semi-tractor trailers that long. Imagine that. So we get rebar in 60-foot lengths maximum. And basically, that's 3 separate rebar cages that all had to be spliced together. And we actually use mechanical splices, just like you were talking about. But 3 separate columns, splice them together to make one long enough. Actually, the casing, we do the same thing. We actually weld the casing, stick another on top, and have a guy out there welding it in place. Set it, do the same thing again until they get the length they need. Oh, this one, so Steve asked me to do this, and he wants stories, because I'm like the cool guy. No offense. But so a lot of these pictures are just fun from the site. This guy right here, Bill, you can see him in that picture because he's always conducting, right? He's a very experienced foreman that we had for the crew from R.W. Harris did this work. And I loved it because he was literally the conductor out there. So I call him the maestro. He had one hand flagging the crane operator. He had the other hand telling the guy on the vibrator what to do, because it's all happening at the same time. I've got the cranes pulling the pump and the trimmy out. I've got, sometimes it's the vibrator pulling the can, and I've still got this going on, filling it with concrete as we're pulling it. And he would always have one thing doing this and one doing this, and he's just out there conducting. I loved it. Hell of a guy. He was very loud. He was really fun to work with and excellent at his job. He really had a touch. He could say, I got a feeling this one's going to do this, and he was right. Interestingly, we talked about the sinkholes and everything else and causing a cave-in on the work site. So when we had these things vibrating in the ground, we were always cognizant of the ground and making sure we didn't see any depressions or stand too close to that operation. Really quickly, just to show you the pile cap or the pier cap, what that looks like. Again, you can see the top of the pier here with the rebar coming out. This is now the cap that's going to transfer the load. Same thing here. You see a larger one with several of them that happens too. All right, this one's an easy one. Everything goes right or wrong on a construction project, true or false? Everything always goes according to plan. The great philosopher Mike Tyson once said, everybody has a plan until they get punched in the face. Remember that, write it down. So things don't always go as planned. This is where the stories happen. I'm going to get through them quickly because I know everybody has other plans as well. We go through the whole operation. We get the rebar cage set, and Matt puts that tape back down. And over the past 10 minutes, you've had settlement in the bottom and you have what's called a soft tip. Guess what you get to do? You've had sedimentation 8 inches thick in the bottom of your pier. Hook everything back up, take it all back out, clean it out, and start over. So it happens. The guys on the crew hate it, but it happens and you do it. So this is one that was interesting. This is one of those boring logs like we talked about before. You can see the blow counts. You can see the different layers. What you also see is a wash layer to 25 feet. And what that means is they didn't actually sample that material in the first 25 feet because it's really not important when you're putting a deep foundation in. However, what we did not realize because of that was we hit a layer 15 to 20 feet down of but it wasn't. It was super clay. That's what I call it. We hit a clay layer that was so hard I couldn't squish it with my boot. It was just rock solid. But we couldn't vibrate the cans through it at all. So we had to punt, modify our methodology. We had to basically set a larger can and pre-drill those holes just to get the can through it, the casing through it. So one of those things, it was a little bit odd. Everybody was surprised. You know, Bill, who's done this for 4 years, has never seen clay quite like that, in this area, but it happened. And this one is what, kind of like with the grouting, you never know when you're done. It's the same thing with these. You can't stop pouring it or else you have to abandon it, and it's very expensive at that point. So you basically pour it until it's done. Sometimes you hit a void, sometimes you don't. This is a curve that the test lab made that shows you the theoretical volume. So if you actually measured the cylindrical volume of a pier, that's what it should be. This is the actual. That's pretty close. So that's good. That's what you want to see. That's pretty typical. All right? This is less good. So now what we've got is one that basically took, I guess it was supposed to be 9-ish cubic yards volume. It took 18. So that took 200%, It's not great. We're not happy when it happens. Makes for a long day, but it happens. This one's really bad. So what you'll see here where it dips back, what this is indicating is a very good day until you start to pull that casing back out. And as that casing comes back out, we hit a point where there was a void outside of that casing and all the concrete went. So you go negative, and you had concrete poured up above the ground, and all of a sudden it sucks down, disappears. And you pour another truck in because that's what you have to do. And instead of coming up, it doesn't come up. And another truck. We wound up there at about 9 o'clock at night. That one took 500%. Okay. And here's the part that was nuts: was we were literally on the last truck of the night because they have DOT restrictions on the drivers. They have so many hours and they can't drive anymore at the concrete plant. Last truck, this is it. Either makes it or it doesn't. And it stayed. And Bill was high-fiving everybody, and we all kind of had fist bumps, and but we were that close to losing it. We were on the phone with GA going, man, what do we do? So it happens. So here you go, theoretical volume of that. I think it was drilled shaft, I don't know, number 9. 8.7 yards, took 52 yards. 9 p.m. we were done. Those two were the same day. So that was a long day. We're going to skip this because you guys already talked about it. So real quick, these are some easy pictures to show you where we're at now. This is when we were doing the drilled shafts. You can see now the shallow foundations and caps, basically. Here we are right now. We're halfway through poured with the 5th floor. You guys can see it across the street, obviously. You guys were all touring it the other day, so you're aware of that. People online obviously have not. And what's next? Here's what we're doing now, guys. We actually have the whole thing built through building information modeling. So doing a lot of the coordination. You can see everything that's going in that building is modeled, and we pre-coordinate everything that way. Some of the tech we're using, we're laser scanning some of the things on the slabs. So you're actually seeing the model overlaid with a laser scan. What's circled is a very small issue, and that's how we identify issues a lot of times before we finish the work. Here's an aerial photo. We're using aerials with drones as well as a quality control check. So same thing, we do an overlay. You can see somebody's gone through and said the things are good. And here's what the beautiful finished building will look like. You know, I think you guys have all seen these. This is where we're all going to be hanging out, you know, in another year and a half here. So I'll be, I don't know, I'm in there somewhere, I think. And there's another question. Which of the following tools can be used for quality control on construction projects? You always choose all the above. Steve, I'm going to turn it back to Mr. Steve Lafferty, I believe, to wrap this up. Maybe? Maybe not. Guys, thanks for the time. We'll see you again on site soon, and somebody in here might be in the next class as well.
One interesting story I heard before I actually came to USF, they were building the Laurel Drive garage over near the medical center. And this was when they first decided they're going to try deep grouting. So they pumped it and they pumped it and they kept pumping, and they didn't figure out let's just pump 20 cubic yards first. They just pumped and pumped and pumped. I think they pumped over 1,500 yards of concrete into the aquifer. On that project, it was about $1.5 million of concrete that just floated away into the aquifer under there. But so now we stop at 20 cubic yards, 2 trucks, let that harden a day, and then come back to it. So that's how scientific construction is sometimes. Okay, so I know the class in here had a bunch of questions through the other day. No? Okay, Jacob.
When there were the models you showed on the screen of like the drillings, there's always this one drilling underneath the staircase that was colored either like blue or yellow. Why? Yeah, I was wondering why that was.
Alex, any idea for that? Nope. There was maybe that was just a bigger one than all the others. Yeah, it's one of those. That's the art in the art and science. All right. Okay. Let's see if we've got any questions online here. Let's see. Questions. Anybody online? Just type in your question. Nobody yet. All right, come on, guys. Did you have one? That was almost a raised hand, but not it. Okay. Yes. So the question was, let me repeat it for the people online. So the question was, when you can't use the vibrating machine to get the casings down in there, what do you have to do?
We wound up re-drilling them with a larger auger bit so that then we could insert the casing beneath that, and we only pre-drilled through that first layer. Now there's other ways to do it. You can put basically a drill head on that casing and twist it in. It adds money, it adds time, things like that. So you have to analyze it. I'm sure James could tell us 50 other ways to do it. But you know, everything on these sites is figure it out. There's always a solution. Some of them cost more, some of them take more time, but you know, working together usually with the engineers is how we resolve them. You know, and that's what we had to do in this case too.
Okay.
I guess where you run into that more often is if you're going to do an expansion to a hospital per se. You know, they might be doing surgery, so a lot of times for something like that, we'll switch it up. We'll do like micro piles, which get installed a little bit smoother. They don't make as much vibration, and you also have to coordinate with the hospital, and there's just a lot that goes on. It gets kind of crazy sometimes, but yeah, you got to coordinate with the hospital and use methods that are going to benefit what you're trying to do. But there's always a way to get things done. You just got to figure it out. That's part of the job.
Okay, any other questions? So we did run over about 5 minutes. I apologize. So if you've got any questions, just shoot me an email, slafferty@usf.com. Nobody's popping in online. All right. Thank you all very much. Hope it was interesting. Thank you guys very much for taking time out of your day.